Before we get into the video, I want to give you all some context. I have been sitting on this idea for a long time now, and this video by Joseph Newton finally gave me the push to start working on it. You should check out his video as it provides a really in-depth and rigorous motivation for a lot of concepts that appear in category theory. But, as is this channel's philosophy, we're here to do something silly. This part of their video stood out to me.
A lot of mathematics involves taking an intuitive idea, formalizing it, and then realizing that the formalization leads to results that are completely rigorous but counterintuitive. That's why the rigor is important.
I agree with them that rigor is important when setting up the field, but in this video I want to focus on the other direction, where we try to understand the already established formalisms through a simple intuitive example. So the video is gonna go like this. We will talk about the secret sauce that made category theory click for me, and we'll see how far we can stretch it. Then we will talk about how this actually is related to Joseph's example, and then use category theory to prove some number theory results. Finally, we will discuss some limitations of our example. A category has objects which we will represent by dots and morphism between those objects which are represented by arrows. The idea of a morphism captures how one object morphs into another. We take our objects to be natural numbers with 0 and we draw an arrow from A to B if A divides B. As we have 6 divides 24, we'll draw an arrow going from 6 to 24. We can label this morphism arrow with the number 4, showing that 6 morphs into 24 via multiplication by 4. But I'll omit that for clarity sometimes. Morphisms can also be composed, as in put together. 6 divides 24, which itself divides 48, and this can be written with a single morphism denoting 6 divides 48, where the label of this morphism is just the previous two labels multiplied. Throwing all the numbers down and putting arrows between them, we get a category which we nickname div out of affection. As 1 divides every number, there's an arrow from 1 to every number. An object with morphisms to every other object is called an initial object. As every number divides 0, we have arrows going into 0 from every other number, and such an object is called a terminal object. Each object also has an arrow to itself with the label 1, but that is too clunky to draw, so I'm not gonna. Scanning left to right, you can see that the numbers increase in size. So in some way, 0 is the largest number in this category. Weird. Anyway, if we start with two numbers, say 24 and 30, then any number that divides both of them will shoot arrows into both of them. This number is called a common divisor. All common divisors of 24 and 30 you will see also divide 8. In general, if you pick a common divisor D of A and B, then D would divide this special number G. I know that you know what G is. Yeah, it's the greatest common divisor. So any divisor of A and B is also the divisor of G, the GCD. If you pick up any book in category theory, you'll find that this construction defines what is called the product of A and B. The product is a unique object which stands before A and B like a bodyguard. So if you want to go to A and B, then you have to go through, or as category theorists say it, factor through G. Flipping all the arrows around in this diagram gives us what is called a coproduct. Now, A and B are dividing C, so C is a common multiple of A and B. This name is a giveaway because what now stands in the middle is called the least common multiple, or the LCM of A and B. So if A and B divide C, so does their LCM, which gives us this diagram. And yeah, that matches the definition of the coproduct. So we formally say that in the category div, the product of A and B is the GCD of A and B, and the coproduct is the LCM. What we did just now was to make a technical construction in category theory feel more intuitive via arithmetic. Now, we are going to use our newfound knowledge for nefarious purposes. First up, consider this ugly equality. If you want to see a proof of this, I have linked it in the description. But if you believe me
and are ready to do my bidding,
then look at this. Write the product as A times B and the coproduct as A plus B. This is just notation. So with the GCD being A times P and the LCM being A plus P, we can rewrite this equality to now look like this, which is just the distributive property we know and hopefully love. Now I want to offer you something in the middle, which is kind of unintuitive on both sides. Take this identity from Wikipedia. This is the symbol for the product, and this is the symbol for a coproduct of many things. In our case, HOM of two numbers A and B is defined as B over A when A divides B. Interpreting everything in terms of GCD and LCM from what we discussed before gives us this identity. I want to prove this identity for you in the video and not just pawn it off on my blog. But to do that, we gotta talk about Joseph's example first. In that video, Joseph introduces the category int, where all objects are integers, and there is an arrow from A to B if A is less than or equal to B, which can be drawn like this, but it's a mess, so I will only draw this and the rest of the morphisms you can obtain via composition. I will also restrict int to be all natural numbers, including 0, and call this new category nat. If A divides B, then each prime in the prime factorization of A has a smaller exponent than it does in B. Let us look at an example. If 12 divides 360, then each prime in 12 has a power at most that in 360. So if we just isolate the powers and look at them, they all sit inside the category nat. So our boy div, hey div, is equal to the product of categories nats, 1 for each prime. You can show that if A and B have these prime factorizations, then the GCD of A and B has prime factorizations where we take the minimum of powers for each prime. And from the video, we know that the minimum is the product in nat, just like GCD is in div. Similarly, LCM is found by taking a max for each power, which, you guessed it, is the coproduct in nat. Okay, now let's go back to our identity relating the products and coproducts, which we rewrote in terms of GCD and LCM like this. I'll prove this in the case when n is equal to 3, but the exact same proof idea applies to any number of xi's. It's just easier to write. So we write it like this. I'll write the lowercase variable with subscript p to denote the power of p that appears in the prime factorization of the corresponding uppercase variable. I'll also use this symbol to denote that we are taking a product over all primes. It is now time to use our nat inspirations to write everything in terms of prime factorizations and minimums and maximums. On the right hand side, if you want to minimize the difference, then we should subtract the largest amount possible, that is, the maximum. This is exactly what the left hand side says. Now we have proved this identity, which, to be honest with you, I didn't really know before making this video. Hopefully, I have given a convincing enough spiel on how this toy model can help you interpret some advanced category theoretic ideas into simple arithmetic. Not only that, we saw examples where the category theoretic constructions illuminated this toy model and gave us some pretty cool identities. This simple to and fro from examples to abstraction is one of the reasons why I really love math. But oh well, all is not divs and nats in the real world. In our case, from one number to the other, we had exactly one morphism, but that is far from true in any other category. This also means I can't really explain what an equalizer is to you, because that guy needs two morphisms. Your examples can be either simple or broad. If you're willing to make that trade-off, then great, you'll be rewarded with intuition. And you could make small changes to come up with a similar toy model that can capture even more ideas. Let me know any cute category theory facts that you can prove using this toy model or something else that you come up with. Thanks a lot for watching, and here's the outro song. Category theory has so many constructions. I ask you to convert them into simple functions, like the GCD or the LCM, because we better understand them. You say it's hard, it's category theory. Well, here's the LCM and the GCD. They're easy, they're simple, and I hope that you're into it. We will sacrifice some rigor, but it will help you into it.